All right, let's move on to talk about dark matter. So dark matter is something we have really strong evidence for at many scales at this point, not just the classic galactic rotation curves, but from CMB observations, from galaxy cluster structure from many different scales. We have good evidence for particle dark matter. We know the abundance is about 5 times that of ordinary matter. And we know it's dark in the sense that, first of all, it has to have no electric charge from a variety of constraints, including indirect ones or cosmological constraints. But more than that, we know at this point from experiments searching for dark matter collisions with ordinary matter, any direct interaction with the standard model is very small. So this is one of the standard sketches from the PDG review above. So cross sections sort of below 10 to the minus 40 centimeters squared. The cross section for just simple exchange of a Z boson, which is a pretty weak force, is somewhere way up off the top of the plot. So this is very, very weak indeed. And this brings up a puzzle, and the puzzle is, why are the dark matter and ordinary matter abundances so similar? Why do they have anything to do with each other? 5 times might not sound that similar to you, but on a sort of cosmic scale, if you follow the evolution from the beginning of the universe of the abundance of matter versus radiation versus dark energy, this is a coincidence. This is approximately the same. And there's no reason for that to be true if they don't interact with each other other than gravitationally. So this is what's known as the cosmic coincidence problem. That's the sort of overview of dark matter in general. Now let's talk about composite dark matter. So the one constraint I haven't mentioned at this point is that in addition to being dark, but also somehow talking to us in the early universe, dark matter also has to be stable, right? And again, from a variety of constraints, the amount of dark matter is not changing significantly over time, so it has to be stable over the lifetime of the universe. And so those are sort of the things we have to keep in mind if we want to build a model of particle dark matter of what it might be. And there's 2 instructive examples from the standard model of particles that satisfy some of these properties, but not all of them. And the first one is the proton. The proton is cosmically stable. And the reason that it's cosmically stable is essentially due to accidental symmetry. So, for example, if the proton was going to be unstable, it would have to decay into something. We suppose that we only have the standard model, it has to decay into something else in the standard model. So, for example, we could have a proton to say, positron, a photon, just as one example. How would this proceed? Well, we can try to draw a Feynman diagram for it. We know a proton is actually 3 quarks, so it's a UUD composite. And we can imagine there's some kind of, again, 4 Fermi operator that turns those 3 quarks into a single electron, positron. And then we can just emit a photon anywhere. These things are all charged, so we'll just emit it off the electron line. Okay, so there's an operator. It satisfies, or there's a Feynman diagram that satisfies all the gauge symmetries of the standard model. We just need this 4 fermion operator sitting at the middle of it. But if we try to write that operator, it is a 4 Fermi operator. So as we've seen, this is dimension 6, so it has to be suppressed by some high scale. Okay. And so this operator, if the standard model has a very high cutoff, if it's good up to the Planck scale, let's say, and this cutoff is at the Planck scale, the quantum gravity scale, then the lifetime for this process will be longer than the age of the universe. Okay. And there's no, so this doesn't rely on a gauge symmetry or anything like that. This is why this is called an accidental symmetry. It's something that's allowed by the gauge symmetries of the model. It just so happens that if you write the operator down, the dimension of it is too high for it to exist in a renormalizable theory, and it's suppressed by whatever the cutoff is. Another way to think of it is, if you think the standard model is an EFT, this has to come from, this cutoff is the scale at which whatever new physics appears is. So we need new physics for this to proceed. Okay. That's one example. Of course, the proton is a very bad dark matter candidate because it is charged. There's one other example, which is, of course, closely related, which is the neutron. So the N0 is neutral, of course, but it's also charged. And what I mean by that is, of course, the neutron is made of quarks, so I can write down an interaction, an N bar with a photon. If I sort of zoom in on this, this diagram, there's really these three quarks coming along, and I can connect the photon up to those. Okay. So this still doesn't give me a tree-level photon interaction. This will give me an effective interaction. I can write down something that looks like n bar, let's say gamma mu, n d nu, f mu nu, to couple this to the photon. This is once again a higher dimension operator, right? So this will be a 1 over lambda squared. This is suppressed. This time lambda will be the scale of QCD. And through this sort of operator, although the neutron doesn't carry any tree-level charge, it can still interact with a photon. And particularly, this interaction will be active whenever the photon has enough momentum to probe the internal degrees of freedom. You can see that from the operator itself, because the operator has these derivatives in it. One in here and one in f mu nu. And those derivatives will give you strong momentum dependence of this interaction. Okay. So on the lattice QCD side, we'd call this a form factor, electromagnetic form factor for the neutron. But the important point is that this gives a way for a particle to be neutral at tree level, so it has no leading interaction with the photon. At low energies in particular, the interaction turns off, but at high energies, or better yet, in the early universe when there are no neutrons and this is just a plasma of quarks and gluons, then we have full strength interactions with the photon. Okay. So the neutron's a nice dark matter candidate, except, of course, it's not stable. It decays pretty quickly. But this brings us to the idea of composite dark matter. We try to cook up a strongly coupled dark matter sector that will have composite states, which will have the features of both. So there will be a single particle which has both the stability of the proton and the neutrality of the neutron. But at the same time, we can have interactions with the standard model present, in particular in the early universe when these things are deconfined. Okay. So that's the basic idea, the basic motivation. There's a possible bonus to all of this. There are some hints that there's some galactic scale anomalies that sort of say that dark matter might be interacting with itself and might actually be pretty strong. And if those hold up, then strong self interactions are something you get for free very naturally out of a composite model. The jury is still out on that. There's more sort of work on the astrophysics side, but I simply mentioned that might be an additional motivation for considering composite dark matter. Okay, so just very quickly, I want to sort of give a review of what kinds of candidates you can have. So there are many different kinds of composite states that you can identify. You can try to use as a dark matter candidate. People have done all of them. Let me run down the list. So mesons are one example. So Q bar Q state. And this sort of comes in two different flavors. There's an important parameter, which is MQ over lambda C, basically the ratio of the mass of the quark Q to the confinement scale of the theory. And if this is small, then these are pion-like states, where you get pion-like states, and those tend to be used as the dark matter. If this ratio is large, the quark mass is pretty heavy. This gives you what's called the quirky dark matter regime, so quark instead of quark. And so you can make these states work often, especially if you're working with pion-like states, for example. They'll be the lightest composite states in the spectrum, and so you can sort of stabilize them by virtue of there being nothing for them to decay into. Except you're not as protected by accidental symmetry. So accidental symmetry in this case only protects you up to dimension 5 operators, and it turns out that these are not stable enough. So if any dimension 5 operators instead of 6, as for the proton, are allowed, you end up with decays that even if they're suppressed by the Planck scale, these don't end up being long-lived enough to live for the entire lifetime of the universe. There are model building ways out of this. So there are successful models of meson-like composite dark matter that have some additional symmetry constraints that kill these dimension 5 operators. But if you don't do that, this doesn't work. That's one of the weaknesses of the meson construction. Another possibility, which is sort of what I was alluding to with my initial example here, is using baryons or baryon-like states as dark matter. So this would be QQQ. The exact structure depends on what the composite theory looks like. Could have more of them if you have more colors, for example. These are great as dark matter candidates. They're highly stable. As NC increases, you just further and further suppress, due to accidental symmetry, the operators that could let these things decay at all. The main downside to these, which is not such a downside for us, is that you really need lattice to make sense of them. So for mesons, they're kind of nice if you're a model builder because you have access to chiral perturbation theory, effective theories that you can sort of play around with. Baryon dark matter, you really need lattice to understand, or to make a lot of progress on understanding them quantitatively. And the third interesting possibility I'm going to mention are glue balls. So these are pure glue bound states. And of course, in QCD, these are really kind of squishy, broad resonances. But now we're not constrained to be in QCD. We're now existing in any kind of hypothetical theory we can construct. And if we change the parameters of this theory such that the confinement scale is way below the mass of all of the fermions, then you'll have some very heavy meson-like states that you don't care about. But then at light scales around the confinement scale, it's a pure gauge theory. The only bound states are glue balls. And you can arrange for the lightest glue balls to be stable. And now that might not be so obvious, but glue balls, once again, are actually stabilized by an accidental symmetry, it turns out. And essentially, when you try to write down operators that will let them decay, the lowest dimension operator you can write down for glue balls, for example, is this trace over combination of gluon stress tensors, G mu nu, times what's called the Higgs portal, H dagger H. And this is already 1 over lambda squared, it's dimension 6. Okay, so no worse than the proton in terms of accidental symmetry stabilization. This is the most exotic possibility. These are very difficult to work with in terms of model building. The appealing thing, or the reason I mentioned them at this school in particular is, if you're interested in these things and their properties, you want to do lattice simulations, you get to do pure gauge simulations. And you can do things a lot more efficiently thanks to that. Yeah. So there's sort of less pure model building work to motivate this, but from the lattice side, this is pretty interesting because you can attack it with pure gauge methods. And some things are known already, right? So the spectrum of pure gauge glue balls in large N is already known. Some things about matrix elements are known. More exotic, difficult quantities like, say, glue ball scattering. To my knowledge, no one has really looked at that. Okay, so finally, a few words about interactions with the standard model. For direct detection, we get to interact through the standard model force carriers. And through operators that are higher dimensional and suppressed by derivatives. Okay. So I think, yeah, I'm not going to go into too much detail over this, but so for example, if I wanted the interaction of a chi dark fermion with the standard model photon, there's a variety of operators I can write down to accomplish that. So chi bar sigma mu nu chi f mu nu turns out to be the lowest dimensional one. This is 1 over lambda. That's the magnetic moment operator. I can keep going to higher dimension. The one I already wrote down for the neutron, of course, I can write down again here. I put a gamma mu in between my chi bar chi, and then a derivative, and then f mu nu at the end, 1 over lambda squared. This one's called the charge radius. Or I should say, these interactions are functions of momentum. The names of the things, these are the names of what the form factors are equal to at 0 momentum transfer. So the q goes to 0 limit for the photon, gives you the magnetic moment, the charge radius, and so on. You can keep going like this. I can write down similar looking interactions for gluons. I can write down interactions with the Higgs boson, like the one I wrote for the gluons on the previous page. I don't want to go too far into the details right now. But of course, these are all things that we can approach on Lattice. These are all form factors of various kinds of these dark matter composite states, and these are things we can look at using Lattice methods. Last thing I want to say about composite dark matter is about collider searches. I just want to say that there's something unusual about composite dark matter, which makes it very different from all other kinds of dark matter searches. So here's a really quick diagram. So imagine I have some new physics sector and it has a bunch of energy levels in it. So these are new particles that I can go search for. Very generically, if there's a dark matter candidate here, it's probably the lightest state in the spectrum. So for example, in supersymmetry, supersymmetric extensions of the standard model, the dark matter candidate is almost always the lightest state in the spectrum, right? Because there's some symmetry which is common amongst all these new physics states, supersymmetry in this case, and the thing which is stable is some remnant of that sort of survives at low energies, and the lightest state in the spectrum is the sort of preserves that symmetry, is unable to decay into the standard model particles because of that. Okay. Any of these heavier states will generically decay into all the lighter things, and so dark matter has to be at the bottom of the spectrum. And this motivates ways you search for dark matter at colliders. You can look for sort of missing energy coming out of cascade decays of heavier things. In particular, you can hope to look for this even if you can't see the heavier things in the spectrum yet. For composite dark matter, the situation can be very different. And in particular, if it's baryonic, you can have a baryon sitting sort of in the middle of the spectrum of new states that you would find, and mesons that are lighter than the baryon. And this is stabilized. It can't decay into mesons, just thanks to baryon number, accidental symmetry again. And so no longer is the dark matter the lightest thing in the spectrum. So a lot of the generic searches that claim they're looking for generic signatures of dark matter in colliders, they don't apply to composite models. The other thing to point out is that if I look at these light states in the composite model, some of these are almost certainly charged. If I have any kind of interaction with the standard model, right? So if I want to have, say, these dark matter interactions with photons, that means that the dark quarks have to carry some electromagnetic charge. And even if the dark matter candidate itself is neutral, there will be some other rearrangement of them in almost every situation, which has a tree level electromagnetic charge. Yeah, and then you can go look for like pair production of these things, whatever this is, state X, X plus, X minus, just being produced. So even from old experiments at LEP, so old E plus E minus collisions. Okay, and you get strong constraints on the sort of minimum scale of this entire dark sector. So I didn't label it. This is composite. You get strong constraints from on where the bottom of this can be from experiments like LEP and from the LHC. Yeah. So generically, and this is not a completely true blanket statement, but in general, for most composite models, the dark matter tends to be significantly heavier. Sort of has to be at the TeV scale or above, but that can be accommodated. Okay, so just to wrap things up, a few words on a couple other scenarios other than composite dark matter. So the one that I really want to mention is neutral naturalness, and this is another solution to the Higgs hierarchy problem. And a lot of the solutions to Higgs hierarchy rely on some new symmetry appearing, and that sort of gives a cancellation of these loop contributions that lead to the hierarchy problem. That's sort of, very roughly speaking, how low-scale supersymmetry works. And neutral naturalness models do the same thing, but they use basically the simplest possible symmetry, which is Z2. Okay? So the idea is you take a twin copy of the standard model, sometimes known as a mirror copy. They're connected through the Higgs sector, otherwise they don't talk to each other. And because you have identical counting factors from the standard model and its twin, you can get cancellations of these sort of Higgs mass loops. Right, so I have my Higgs loop at the top. I'm going to have an identical Higgs loop with some partner top prime. It's a mirror partner that's on the other side. And these don't look at face value like they're going to cancel, but part of this is, I have to add an additional, the Higgs sector is not a single Higgs boson. There's sort of a pair of doublets that are connected to each other. And overall, the hierarchy problem, the problematic diagrams will cancel each other off, okay? And this neutral naturalness is so-called because the twin states carry SU3 twin color, but not ordinary color. And that makes them much harder to produce at the LHC compared to the supersymmetric states that you get in supersymmetry all carry ordinary SU3 color, and so you can make them really easily at the LHC. Yeah, so that's the neutral part in neutral naturalness. So these models get a decent amount of interest from the phenomenology side. I think they're really interesting from the lattice point of view because generically this is a twin sector. It looks almost exactly like the standard model. In general, because of the difference between the Higgs vacuum expectation values, the twin Higgs will have a heavier VEV, and so there'll be heavier quarks on the twin side. But otherwise, it looks like a copy of the standard model, and you have a copy of QCD at low energies, just with heavier quarks, right? And there are a lot of old lattice QCD results that were done out of necessity at relatively heavy quark masses, and they're all potentially relevant for these neutral naturalness theories. So I think that's an interesting connection. A little more narrow maybe than some of the composite Higgs, composite dark matter kind of, we're exploring the space of theories. This is a much more specific connection, but I think it's interesting and worth mentioning nonetheless. Okay. Finally, there are other models, other BSM ideas that have lattice efforts. Just due to time, I can't go into any of this. There are efforts to put supersymmetry on the lattice, which I would say have been largely successful. This is a difficult thing to do. You can ask me for a review of that. Large extra dimensions, so having more than 4 dimensions in your theory, which is related to other ideas to solve the Higgs hierarchy problem and have physics beyond the standard model. There are lattice simulations along those lines, 5-dimensional theories. Quantum gravity, there are lattice models of what's called dynamical triangulation. I will not go into details about it all, but I can point you to if you're interested in. And then chiral gauge theories, grand unification. There are fundamental obstacles to putting chiral gauge theories on the lattice. There are no-go theorems, but people have that has not stopped people from trying to get around them and try to say things about these concepts non-perturbatively. There are attempts in those directions. And then on the side where there's little to no lattice work, but where I think there could be, there are a handful of these kinds of models out there, and I sort of mentioned them so you know the keywords to look for. There are models of composite neutrinos, so giving neutrino mass by coupling to a composite sector. Composite axions, either to solve the strong CP problem or just more generally. And then composite quarks and leptons, so the idea that everything in the standard model could be composite. This goes under the names of preons, typically. These theories are really, really badly constrained, and I think the kind of dynamics they assumed or tried to use to build these theories in like the 80s are not supported by any lattice simulations that I know of. But who knows if a new idea might be able to make some breakthrough in this field. So I mentioned the possibility too.